Okay, so in this talk, I'm going to consider the situation where you have a function of two variables and you have the graph of the function, and now you want to restrict the behavior to some two special cases. One is where you fix the y value and you are thinking of it as a function just of one variable x. So you're restricting to a particular value of the y coordinate and allowing x to vary. The other is where you fix the x coordinate and allow the y value to vary, and you're just thinking of it as a function of one variable. So after you do the restriction, this restriction, how many variables is it a function of? One, right? Because this other variable is 6. Now, I have the picture out here, not labeled anything here yet, but so this is the xy plane. And the domain of the function is a subset of this plane. What does that mean? Any point in here is a potential input to f. Now the domain need not be all of the plane, so you could have points which are outside the domain, but points here are just potential inputs. The graph of the function would involve a third axis. So it would be, there'd be a z-axis, and the points on the graph would be basically you take a point in the domain and you look in the z-axis parallel line through the point, you pick the z value according to the function value at the point. Okay? Now, what does it mean to say I want to restrict to y equals y naught? Well, first of all, what does a line like y equals y naught look? Well, you're fixed to y and you're still allowing x to vary. So what kind of line will it be? Will it be vertical or horizontal?
Horizontal.
Horizontal. Great. So it could be a line like this. Okay. Now, how do you find this function? So this function is just the function which sends x to f of x comma y naught. Okay. So it's just now a function of one variable. What's the graph of this function of one variable in terms of the graph of the original function of two variables?
What do you mean?
Well, I have this graph of a function of two variables which look like some kind of surface, probably in R3. Okay, it's kind of living up here somewhere. And now I want to use that picture, just pictorially use that to figure out what the graph of this restricted function is. What should I do? I should intersect that graph with what plane?
With the plane y equals to y naught.
Yeah, so there'll be a plane something like this, y equals y naught. And now since now y equals y naught, we're doing in 3 dimensions, it's actually a plane. Okay, it's a plane with one axis along y equals y naught that's parallel to the x-axis, and the other axis parallel to the z-axis. So it's a plane parallel to the xz plane. Okay, so intersect the graph with the plane y equals y naught, which is parallel to the xz plane. And now in that plane, that intersection is just the graph of this function. What function? Function which sends x to f of x comma y naught, where you just set this point as the origin. So you'll have a plane like this, and you'll be setting this point as the origin. This z-axis is the function axis, and this axis, which is parallel to the x-axis, is the input axis. Okay, and so you'll get a picture of a graph, and that you can interpret as a graph function of one variable. Okay, what about the other case, restriction to x equals x naught? So let's say x naught is this number here. So what does the line x equals x naught look like in this plane? The line x equals x naught will be a vertical line. Okay.
Yes.
Now what would the restriction look like? What would the graph of the restriction look like in terms of the graph of the original function?
Another plane.
Another, well, you'd have to intersect the graph of the original function with a plane. What plane would you intersect it with?
X equals to x naught.
Yeah, x equals to x naught, now viewed in R3, right? X equals x naught, if you just view it in R2, it's just a line, but if you view it in R3, it gives you a plane. What will that be parallel to?
YZ plane.
Yeah, and the y-axis parallel thing in that will serve as the input variable, and the z-axis thing in that will serve as the output variable. Okay, awesome. So now you can tell me quickly, we have seen this notion of separate continuity. And what does that mean? What does separate continuity mean? What does it mean for a function to be continuous in one variable? Like if I give this function f of x, now what does it mean for it to be continuous in x?
Fx, y as x approaches.
Well, you can just assume you know what continuity is in one variable. So it just means that this function, so continuous in x, let's situate at a point, or not, let's see. Continuous at a point. So continuous in x at a point x naught y naught. What does that mean? What function is continuous? This function. So just say the full sentence.
Limit of.
No, don't say it in terms of limit. Just say it in terms of continuity. So this function. I mean, you can also say it in terms of limit, but we don't. This function is what?
I don't know what you want.
This function is continuous at what point?
X naught, y naught.
Well, now it's just a function of one variable, so at x equals x naught.
X naught.
So what I'm saying is this function of two variables is continuous in this variable at this point if the function of one variable you get by fixing the other coordinate
Okay.
is continuous at x equals x naught. Okay, so just a reminder, and similarly you can do continuous in y. I won't write that. Okay, continuous in x everywhere. What would that mean? Means the above holds everywhere, right?
Yeah.
Well, you have to be a little careful about boundary points. You'll have just one-sided continuity, but roughly speaking, that's the idea. Okay. So, sort of, if you have boundary points, you just have to look at one-sided continuity. Now, what I really want to talk about here is, I'll just write down, separately continuous, whether at a point or everywhere. What does that mean? Yeah?
Not sure.
What does it mean? Well, what should it mean? Separately continuous. It's continuous in each variable, right? But why do I say separately continuous?
Well, you want to say that not jointly continuous?
Yeah, what would jointly continuous mean? Jointly continuous would mean you are using that epsilon delta definition, which says that if you get close enough from any direction, you're close. So this separately continuous just means continuous along the vertical and horizontal lines,
Okay.
right? As you'd probably remember. Separately continuous in both variables means what? Continuous in each variable separately, but it need not be jointly continuous, which means that if you look at a diagonal direction of approach or a curved direction of approach, it need not be continuous. Okay, now what I want to talk about is how does this interact with the graph pictures. So what would it mean to say it's continuous in x everywhere? What would that mean pictorially in terms of the graph? Well, it would mean that each of these intersections you get by planes of the form y equals y naught, for each of those intersections, the graph you get with that intersection is the graph of a continuous function, right? So each of these slices gives you a continuous picture, but the overall picture need not be continuous. I mean, yeah. And similarly, what would it mean, say, to say continuous in y everywhere? Well, that would mean each of the slices of the form x equals x naught give you graphs of continuous functions, but overall the picture need not be continuous. What would it mean to say separately continuous everywhere?
They are continuous.
Both these types of planes, so both the planes of this type and the planes of this type, when you intersect with the graph, you get continuous pictures. Okay, but overall, it's still possible it's not continuous because it need not be jointly continuous. Okay.